Okay, Assalamualaikum warahmatullahi wabarakatuh. Let's continue our lecture. So, you have learned about Faraday's law. For Faraday's law, you have learned that a changing B induces an EMF which can produce a current in a loop. Okay, so in order for charge to move, there must be an electric field. So we can state Faraday's law more generally in terms of the E field which is produced by changing B field. So you have learned for Faraday's law. It's about the induced EMF. Okay, so we have known that for EMF, alright. So for for EMF, EMF, you know that EMF equals to the changes in flux over the changes in time. So the rate of change of magnetic flux. So here we can put the magnetic flux. So this is the EMF. So in voltage. So EMF is the rate of change of magnetic flux. So when there is changing B, so it will induce an EMF, where the EMF will produce a current. So this one the I induce. Okay, and in order for charges to move, the current there must be an electric field. Okay, so we can state that in general terms the E field, which is produced by changing B field. So that's about Faraday's law. Okay. Okay. One example: pulling a coil from a magnetic field. A 100 loop square coil of wire with side L 5 cm and total resistance 100 ohm is positioned perpendicular to a uniform 0.6 Tesla magnetic field. It is quickly pulled from the field at constant speed, moving perpendicular to B, to a region where B drops abruptly to 0. At t equals to 0, the right edge of the coil is at the edge of the field. It takes 0.1 second for the whole coil to reach the field-free region. Find A, the rate of change in flux through the coil, and B, the EMF and current induced. C, how much energy is dissipated in the coil, and D, what was the average force required. So first of all, okay, let us state jotted down the parameters involved. So a 100 loop square coil of wire. So this is the end. Okay, which side L? Okay, so obviously this is the L, but you need to change to meter. So it will give you 0.05. Okay, meter. And total resistance 100 ohm. So this is the total resistance, the R. Okay. Is positioned perpendicular to a uniform 0.6 Tesla. So this is the B, the magnetic field, 0.6 Tesla. It is quickly pulled from the field at constant speed, moving perpendicular to B, to a region where B drops abruptly to 0. So this is the B initial, 0.6, and this is 0. This is the B final, equals to 0. At t equals to 0, the right edge of the coil is at the edge of the field. Okay, it takes 0.1 second for the whole coil to reach the field-free region. So this is the changes in time, 0.1 second period. Right. So you have a few parameters here. You have the N, you have the L, R, B initial, B final, and the rate of time. Okay, the time rates. Find the rate of change in flux through the coil. Okay, so this question asks you to find the rate of change in flux through the coil. So for flux is the change in BA cos theta. Okay, so is either B change, is either B you change there are changes in B, or changes in A, or changes in theta. So for this one, okay, so if you notice in this question, the change is about the magnetic field. You can see that the magnetic field abruptly from 0.6 becomes 0. So this is the changes in B. So for this question, you hit the changes you put here, the changes in B, A cos theta. So equals here. Okay. So let us do this one. Okay. So you have know that. So this question asks the rate of change in flux. So for the A, so change flux is magnetic flux is B A cos theta. For this one, changes in B. Okay, A cos theta. So B here is B final minus B initial, right? A cos theta. Okay. So B final, what is the B final? So here you can see that B final is 0. Okay. So 0 minus B initial 0.6. Okay. Minus 0.6. Right. So A, okay, A for A, if you notice this question, their word in this question state that this coil is in the square shape. So for the square shape, you need you know that the shape for the square is equal, or the length of the square is equal. So to find the A means that this one 0.05 times 0.05. Okay, cos theta. Okay, theta. This question state that the position is perpendicular. Okay, the position is perpendicular to a uniform 0.6 Tesla magnetic field. So perpendicular. So if you notice that, say we have, let's say we have a coil of wire. Okay, so let's say we have a magnetic field B, and the coil of wire is like this. Okay, which is 90 degree to the B. Okay, so this is the coil of wire. Okay, so but the theta is not 90. The theta is the normal line of the surface area. So let's say this is the coil. So you have the B here, which is 90 degree to the coil, but the normal line is here. Okay, so the theta will become 0. Okay, because we consider the normal line. Okay, the normal of the surface area. So theta is close to 0. So this one is cos 0. Right? So you can get the flux here. Okay, in Weber. Okay. B, the EMF and current in use. Okay. Okay. So here you get negative 0.0015 Weber. But if you notice, this question asks you the rate of change in magnetic flux in flux. So that means that you need to find the flux over the changes in flux over changes in time, where negative 0.015 over what changes in time here. You can see that where is the time. Okay, it takes 0.1 second. Okay, this is the T. So it takes 0.1 second. So 0.1. So you will get here negative 0.015 negative 0.015 Weber per second. Okay. Okay, so for B, the EMF and current induced. Okay, so let us do this one. So for B, the question asks you to find the EMF and current induced. Okay, so EMF, we know that EMF equals to the changes in flux, magnetic flux, over the changes in time. Okay, the changes in magnetic flux over the changes in time. Okay, so from here, what you have obtained before, okay, this is, you must put the negative here, so it will give you negative 0, negative in bracket, okay. Sorry, because I just noticed that for this loop we have this one, 100 loop square, so this is the n. Okay, this is the n number of loops, so this is the n. So for the EMF, okay, we can write EMF equals to n changes in flux over changes in time. So for this one, negative n changes in flux over changes in time equals to negative n is 100. Okay, changes, sorry. Okay, so negative 100 changes in flux over changes in time we have obtained in the previous question, in question A. So here we have negative 0.015. Okay, so here you will get 1, 2, negative 1.5. Oops, negative 1.5 volt. Okay, negative 1.5 volt. Okay, so this one is negative 1.5 volt. Okay, right. So I just want to tidy up the writing. So this is the volt. Okay, 1.5 volt. Alright, so this is for EMF. Next one, the current induced. So you have learned before for current induced, V equals to IR. Okay, V equals to IR. Okay, so for the current induced, V equals to IR. Okay, for this question, V here is EMF equals to I, given to you I is I is not given. Okay, so what is the R? R is here, 100 ohm. So this is the R. Okay, so for I, you need to find the I, and R is given. So for I is EMF over R, whereas EMF is negative 1.5. Okay, negative 1.5 over R. R is 100 ohm, 100. So over 100. So you will get the answer. Okay, so this one will give you negative 0.015. Negative 0.015. Okay, and right. So the next question. Okay, for the next question, how much energy is dissipated in the coil? Okay, so for energy dissipated, for question C, okay, for energy dissipated, P equals to I squared R, where for this one I is negative 0.015 squared times with R. R is 100. So you will get here so you will get, for the power, you will get 0.0225. Sorry. Okay, so you will get here 0.025225 for power. So 0.0225. Okay, 225. This one for power, but the question asks you to find the energy. So energy equals to power over time. Okay, so you use 0.0225 over the time is 0.1. So you will get for energy you will get 0.0 sorry 0.225 225. Okay, right. So 0.225 joule. And the last question, what was the average force required for D? So I have to write here D. Okay, so for D, where is it? So for D, sorry. Okay, so for D, you can okay, for D, so we have what was the average force required? So we know that work equals to FD. Okay, so force equals to work over D. So you get here work is 0.225 over D. D, what is the D? D is the distance. Okay, so okay, so we will do again for question D. Okay, so for D, okay, before that I just noticed that this is the unit for this one is not V but A. So it is an I, right? I, so I is ampere A. Right? So this is ampere, right? Okay, so for question D, what was the average force? So what was the average force, the F? Okay, so for D, so we know that for average force, work equals to F D. So F equals to work over D, or energy over D, because work is joule, energy is also joule for this equation. So E, we have E 0.225 over D. D is 0.05. Okay, so you will get uh, 0.225 over 0.05, 4.5. Yeah, okay, right. This is the answer. So I noticed that for this one, there are some correction you need to do here. This is not 50 milliampere. So you can refer to my notes before. That one is uh, 1, 2, 3. 1, 2, 3. Oh, correct. Zero, because this one in ampere. So correct. Negative 0.015 ampere, or 15 15 ampere, right? So for sorry, or 50 milliampere. So for milli times out, we need to divide with the but this one in ampere, right? So I got confused. 15 1 1 2, right? This one ampere. So if we want to divide with the 0.015 from ampere to milli, 100. Okay, so there is correction for this answer, right? This is wrong. Okay, this is wrong, so you need to correct it. Okay, right. So it will affect the question for C and D. Okay, so we move on to the Lenz law. Okay, so for Lenz law, state that the polarity direction of the induced EMF is determined by Lenz law. Okay, it's about polarity. Okay, and in terms of definition, we can see that the the definition is the direction of the EMF induced. So it states about direction of the EMF induced by changing flux. So you change the flux, will produce a current. So you produce a current that generates a magnetic field, that generates the B, opposing the flux change that produces opposing. So you have a negative there, right? So this is the definition of Lenz's law, where it said that we know that from the Faraday's law, when you have when you have a change in flux, okay, change in flux, right, over time, you will produce or induce the EMF. This EMF will induce the current. Okay, so for Lenz's law, it is about direction. Okay, direction. Okay, the direction of the EMF induced. So that we say that the direction of this one, the induced EMF, the direction of the EMF induced by changing this one, by changing the flux, will produce a current. Okay, and these things, or this situation, right, will generate B that oppose the flux change, B that oppose the flux changes in flux. Okay, so B that oppose. So again, from the Faraday's law, you have learned that when there is a changes in flux over time, right, it will produce or induce the EMF, and this EMF will induce the current. Right, okay, that one for Faraday's law. For the Lenz law, it said that the EMF induced, the direction of the EMF induced, okay, by changing the flux, will produce the current that generates the B that oppose the flux. Okay, okay, so this is what the definition state, where we can see that when we have let's say we have a loop here and we have a magnetic field. So what will happen is that this loop will become a temporary magnet, will behave like temporary magnet, where it will have a polarity or poles north and south that will oppose the one that will oppose the changes. Okay, for example, if we move on the magnet, so the magnet, okay, the north part of the magnet closer to the coil, okay, So this part of the coil, we have two part here, okay, to position. This the front part of the coil will oppose the changes, and this part will, of course, to oppose, it will be have will be N, not, and the other part will become S, south. Okay, all right. So this is the Lenz law. So if you want to know what is the direction of the I induced, so you can use the right hand rule, right hand. Okay, right hand rule. So for the right hand rule, so use your thumb to choose the direction of the north, and your other four fingers to show the direction of the I induced. Okay, so right. So you have said that the I your thumb is like this. So the other finger will be like this. So this is the I. So this is the direction of the I. Okay. Right. So I will skip this one. Okay. It's not. It's quite confusing for you, I think. So for this one, for the Lenz law, okay. So for example, okay, this part of the slide shows you the direction of the I induced. Okay, you can see the I induced here. How to find the direction here? So you need to use the Lenz law. So okay, you can see that this magnet is moving away from the coil. So what happens that this coil will oppose the changes. So this part of the coil will be S, and this part will be N. Okay, south and north. So the front part of the coil will be S. So by using your fingers shows the direction of the north, and the other fingers will show the direction of the I. Okay, the current. Okay, right hand rule again. So we will obtain that the I induced here is a clockwise. Okay. Okay. For this part, you can see that N is closer, being put closer to the coil, and of course this part of the coil, the front part will be N, and the behind part will be S, south, because you want to oppose the bulb magnet. And by using your right hand, your thumb will show the direction of the N, the other finger will show the direction of the current induced. So your I will be here, I induced. Okay. Okay. So this is a few examples of induction where we have induction stove, induction cooker. Where I think some of you have this one, where we can, when we touch the stove, we will feel, we don't feel the heat. Okay, we not feel hot and so on, because uh, the stove only will heat the ferromagnetic material. Okay, so those ferromagnetic material, let's say you put you want to cook something, so the food will be heated if you use the correct ferromagnetic material. Okay, for example, here you have pan. Okay, this pan with a ferromagnetic material, so the food will be cooked. But if you touch although this one is hot, but when you touch the stove, okay, you will feel cool, and you will feel cool, and uh, doesn't feel the hotness. Okay, and because inside the stove, okay, if you open the stove, inside the stove there is a coil. Okay, we have a coil. Let's say this is the coil. Okay, so and this coil will be connected to the AC power supply. Okay, so when we have AC, so we have a alternating current in and out. So this one will produce a magnetic field. Okay, and this magnetic field will be have a flux changes in flux over time, because it will be cutting here and there, and it will produce eddy current and produce the heat. So when you put your pen here, okay, so this pen will be heated. Okay, but it must be ferromagnetic material, right? So you can if you're interested in this application, you can search, right? And another application is we have a tape, hard drive, etc. So we have a tiny coil response to change in flux, okay, as magnetic domain, okay. So you can see that here is the coil, okay, and we have a credit card reader. If you swipe the card, it will generate the changing flux, okay. So this is this will produce the changes in flux, okay. And of course, for our electricity, we use this one as a generator, or I think some of you have learned about dynamo. Okay, so when the water turns the wheel, it will rotate the magnet, change the flux, induce the EMF, and drive the current. Okay, so here we have the concept of Faraday's law. Okay, changes in flux over time will produce the EMF and will produce the current. Okay, so generators, okay, to produce the current, we can also use the generators, where generators use the concept of induction. Okay, you can see that when there is here we have a magnet. So for this magnet, you have a magnetic field. So when you rotate the loop, so it will be cutting that here and there at the magnetic field, and there will be a changes in flux. So the changes in flux will produce the EMF and will produce the electric current, and here you can see the bulb light up. Okay. So for inductor, okay. So we move on to inductor. What is inductor? Inductor is the coil of wire. Okay. Right. So a coil of wire that can carry a current, can carry current. Okay. So it be used in the electric circuit because they can store energy in magnetic field. Okay. Store energy in the magnetic field. Okay. So that is the one of the factors why inductor being used in the electric field. Okay, so this is the equation where state that V equals to L di over dt. Di here is the changes in induction. This one the changes in time. Okay, L is the inductance. Okay, and V is the voltage across the inductance, and the unit is Henry. Okay, the unit is in Henry. Okay, right. So this is why the minus sign, because the opposed station. So for inductor, the symbol for inductor, we have known that inductor is the coil of wire. So for the symbol, you can draw like this. Okay, symbol for inductor, right? So inductance, we have mutual and self-inductance. Okay, so there are two types, mutual, and then another one is self-inductance. So for mutual inductance, we have this formula, N flux over I. Okay, changing flux in one element induce EMF in another. Okay, so M is the mutual inductance, N is the number of coils, this one flux, okay, in Weber, and I current in ampere. Okay, so you can see that this is the two coils. So if one coil have changes in flux, or we have a magnetic field here, which will be cut here, so it will have a changes in flux here. So it will produce or induce the current in this coil. So this one we call as a mutual inductance. Okay, same with this one. Okay, we will produce the mutual inductance. Right. So for mutual inductance, this is the basic formula, M N flux over I. Okay, this is the thing that we have learned before about the Faraday's law. Okay, and the very popular application of mutual inductance is transformer. Okay, you have learned transformer in your secondary school, I believe. So for transformer, we have primary and secondary, and we use the AC input. Okay, for example, you can see here we have a transformer here. So let's say this is the primary coil and turns, and this one is secondary coil and S turns, for S for secondary, you can see that this one is the step up, okay, step up transformer, and we use the AC generator, right? So so you can see this is the mature inductance. When let's say you have a current here, and this one, when the current move in the coil, what happens that for the AC generator, if the current move in and out and move back and forth, so this current will produce the magnetic field. They will be cutting, will be produce the magnetic flux. They will be cutting here and there, and then it will induce the EMF here, and it will produce the current. So right. So if you notice that there is no connection between the primary and secondary coil, there is no direct connection. Okay. So this is called as a mutual inductance. Okay. Okay. So this is the for the transformer, for example, we can find the VS, the V for secondary, where we have an NS. Okay. The changes in plug over the changes in time. Okay, actually this one use the basic formula of Faraday's law, where we have negative and flux over time, okay, and changes in flux over changes in time, right? So dividing the above equation, we get, okay, this is the relationship between the secondary and primary. Okay, when there is no power loss, we can write the VI equals to VI. Okay, where this one is secondary, primary. Okay, this is the relationship. Okay, so we can see that the transformer plays a key role in the transmission of electric power. So we have power plant. So you can notice this is the 12,000 volt. Okay, so it's just step up transformer. So sorry, this is very quite high. So when this go to the step up transformer, you can see that the voltage increase more. Okay, and goes to the high voltage transmission line. Okay, and comes to the substation, step down transformer. Okay, step down transformer, so it will decrease the voltage. Okay, and then we have the step down transformer. You can see at your house, okay, at your residential area, there is we call as a TNB pole. Okay, where we have a step down transformer that here the wire carries 240 volt to the household, okay, to the house, right? So in terms of power loss, okay, in this transmission, so we will use the I squared times with R, the current squared times with the resistance of the wire, right? So for the that one is for mutual inductance. Okay, for the self inductance, self means that individual, okay, inductance. So we have a AC generator and we have a coil. So the magnetic field lines were produced by I. Okay, it will produce EMF in the same circuit. Okay, same circuit. Okay. So the formula is L and flux over I. This one for cell. If you can remember the formula for mutual is M and flux over I. Okay. For self, L and flux over I. Okay. So this one for self inductance. For example, ideal solenoid. So for solenoid, we can see here the B here, the B for solenoid equals to mu naught and I. Okay, N is N over L, number of loops over length. Okay, and here is number of loops over length. Okay, I is current. So L, okay, this one is the inductance. Okay, and lastly is about energy stored. Okay, so for energy store, for the inductance, is negative L di over dt times with the I. Okay, negative L di over dt times with the current I. Okay, for the power, because it comes from this equation. Okay, and for energy stored, okay, so energy So is half Li square or negative volt die. Half U in this law is half Li square. L is the inductance, I is the current square. Okay. So thank you. Assalamualaikum.